For the Choose Your Own Adventure lab, I decided to explore the physics of a slinky dropped from static equilibrium with a tennis ball attached to its bottom. I first analyzed the motion of the system using Tracker. I then made a computational model to predict the motion and compared my results. I found that the bottom of my model slinky does indeed stay stationary while the top of the slinky moves downward and collides with the tennis ball. The fundamental principle I used in this experiment was the momentum principle. It states that the change in momentum divided by the change in time is equal to the net force. The velocity update equation is the final velocity equals to initial velocity plus F net divided by mass times delta t. I also used the equations for the force of gravity, which is equal to negative mg, and the spring force, which is equal to negative spring constant times the stretch times L hat. I put the video of the slinky in Tracker to extract my observed position data. I put the origin at the top of the slinky so that it moves in the negative y direction. I also used the diameter of a tennis ball to calibrate the video. I tracked the position of the top of the slinky at each time frame. I also did the same thing for the ball, which stayed stationary most of the time. Since I did not know the stiffness constant and relaxed length of the slinky, I decided to use the spring from the Lab5 video. I used that video to calculate the spring constant, the relaxed length, and its initial position as shown here. The spring constant was 6.87 newtons per meter and L naught was 0.126 meters. Now I can move on to my code. Here's where I inserted the constants G, Ks, and L naught. These are the initial conditions of the system. The ball's initial position and velocity are inserted here, as well as the top of the spring's initial position and velocity. Here is the while loop. The force of gravity on the ball and the spring are inserted here. The force of the spring is inserted here. F net is the net force acting on the ball, and F net spring is the net force acting on the spring. I used Newton's second law to calculate the new velocity and position of the ball and spring. When I run the code, here is what the model looks like. I plotted the observed and predicted position of the tennis ball on this graph. The blue curve is the observed ball position and the red one is the predicted ball position. As you can see, both of these positions remain constant during this time. The difference in the heights is due to the fact that I did not know the length of the slinky, so I initialized the model with the spring from Lab4. Regardless of this discrepancy, one can see that the balls stay stationary. The predicted position starts to decrease because of the different stiffness constant for the spring and slinky. The ball in the model starts to move before the ball in the video. Here is the observed and predicted slinky position. During this time, the top of the slinky has not moved as much as the model, but is definitely decreasing. The reason for this discrepancy is due to the different initial conditions. Regardless, a spring with a ball attached would act the same way as a slinky. The top of the spring would fall until it meets with the ball, which has stayed stationary during this time. Why does this happen? The reason that the balls stay stationary is due to the fact that at the point of contact, the force of gravity and the tension force cancel each other out. The center of mass of the system is accelerating as normal. The change in tension force is not communicated to the bottom until the top has reached it.